Okay, so sorry, I forgot to record the lesson. I'm recording this after school. Here we go. So the lesson for set 99 is differentials. And let's start off with the most basic question, which I'm hoping you can answer. And that is, what is a derivative? I'll give you a second to think about that. All right, now in the class, besides the normal silence, some people finally said something like tangent slope. Now that's fine, and that is true graphically. Analytically or verbally, we can also say an instantaneous rate of change. Now, when I say an instantaneous rate of change, it's hard to have change at an instant when it's one point in time. We typically say change is between 2 points in time, a change in y over a change in x. And then we try and approach change at a time by then moving a point closer and closer and closer along the curve so that the change starts to approach change at a point, maybe this point. When we do that, those deltas become more microscopic dy's and dx's. Those are differentials. dy is an instantaneous change in y. The definition of the derivatives takes that delta y over delta x, or the slope, and takes the points closer and closer together through a limit as delta or the change goes to 0. Now that's done in a couple different ways, but the inside of the definition of the derivative is usually some kind of slope calculation, change between 2 points, change in y over change in x, and then getting the points close together, x approaches a. That's the alternate definition, for example. That's one. But the big idea that we know for sure is that change between 2 points can eventually start to approach change at a point. Now, we do that in AP problems a lot. We've done this a million times where you estimate the change at 3 by approximating change between 3 and some point close by. You could say in calculus, we're using delta y over delta x to approximate dy dx. So delta y over delta x, it would depend on the 2 points. I mean, we could choose 2 and 3, or we could choose 3 and 4 for our change. Let's say we use 3 and 4. F at 4 minus f at 3 over 4 minus 3. That might say that the slope is something like negative 3 minus 7 over 1, or negative 10. We might get a different answer if we estimated between 2 and 3. Now, in this case, then we used delta y over delta x to approximate dy dx. That's in the past. Now today, we're going to go the other way. We're going to use dy dx to approximate delta y over delta x, but then we're going to go one better and say, if I wanted to approximate delta y, it's pretty close to dy. And dy, well, we'll talk about that. Let's go to the next piece of the notes here. All right? If I took this idea of delta y over delta x is roughly equal to dy over dx, and if I multiply delta x over, then I would get delta y is roughly equal to the derivative times some change in x. That right there is the star of the show. Put some stars around that because that is the idea of using a differential to approximate difference or change. Okay, we're approximating change using an instantaneous rate of change at a point. Let's take a look at a problem or two. So imagine if the radius of a balloon was 3 inches, and then it expanded a little to grow by a quarter inch. I should have left that alone. Well then, because of that, then obviously the surface area would change. Now, we could use the change in the radius to estimate how much the surface area would change. Now, it's always the case that students that are good problem solvers say, why even use derivatives in calculus? Why not just say the change in the surface area could be found by taking the area at 3 inches and subtract the area at 3¼ inches, or vice versa. And that would actually be the true change in area. We could do that. Problem is, at higher levels, sometimes that's a little more complicated. In the calculus, because the derivative usually involves one less power, the calculus is often quicker and a darn good estimator. So calculus is used at the higher levels to estimate change. So what we're going to do here is we're going to start with the big idea of today, which is to say delta y is approximated by dy, and dy is the derivative times some change in x. Now, go to the problem specific. Now, in this case, we're not talking about x's and y's. We're talking about the area and the radius. So the change in the surface area can be approximated by dA, and that would be the derivative of A times change in the radius. Now for this problem then, A prime, because the surface area is 4 pi r squared, A prime is 8 pi r. We want the rate at which it's changing at the initial point, so an r of 3. And the radius is going to change by a positive 1/4 because it said it grows. If I look at that then, when I find 24 pi, I'm going to put that over 1 for a reason, and I'll tell you why, times 1/4. This 24 pi over 1 has meaning. That's A prime or dA dr, which is to say it's a rate of change. The area is growing by 24 pi square inches for every radius change of 1 inch. There's a ratio of change of 24 pi changes in area to 1 inch change, or 1 centimeter, no, 1 inch change in radius. But I'm not changing a full inch, I'm only changing by 1/4 inch. So that means the area would only change, instead of by 24 pi, the area will only change by 6 pi. The units on that are change in area, so that's inches squared. So I would estimate that the area changes by 6 pi inches squared using differentials. That's the idea of using differentials to estimate change. It's a rate of change times an amount of change in the independent variable gives you an amount of change in the dependent variable. All right? Hang on 1 minute. Okay, so now on to the next. This is a science application of differentials. If a whole group just tried to eyeball and take a guess at the diameter of a ball, and they found the mean of all their guesses was 12 centimeters, I think your notes say radius is 12 centimeters. Based on the range of measurements, there could be as much error as a 1/2 centimeter. To estimate, if you then use that error in the radius, or use that radius then to make another calculation, say in the volume of the ball. Well, because the radius had error, the volume could have error. Now the question then is estimate how much your volume could be off because of that change in your radius. So the idea, again, of the day, I'm going to keep writing it again and again, is delta y can be approximated by dy, and the differential dy is the derivative times change in x. Go to the problem specific, and in this case, instead of y, we're talking about the change in the volume can be approximated by dv. Now dv then would be v prime times changes in the radius. Now we start making that calculation. V prime, given that volume is 4/3 pi r cubed, V prime is 4 pi r squared. We do that at the initial value of an r of 12. dr is how much the radius could be off by or changed by. That's plus or minus, because we don't know if it's an over or an underestimate error of a half. When I plug in 12, I get something like 4 pi times 144 times plus or minus a half. Again, that's a rate of change in volume with respect to r. That's dV dr. So I would expect the volume to change by something like 576 pi cubic units for every radius change of just one. That's a huge rate of change. The volume changes a lot by just one little change in the radius. If I were to clean this up a little, that is 288 pi centimeters cubed then. Just by changing the radius a half of a centimeter, the volume could be off by or changed by as much as 288 pi cubic centimeters in either direction. Now, that's roughly about 900 cubic centimeters. The next question then, and a logical one, is, was that a lot? Well, it would kind of depend. I mean, if you were finding the volume of a golf ball and you were off by 900 cubic centimeters, that would be a lot of error. But if you were finding the volume of the sun and you were off by 900 cubic centimeters, that wouldn't be a lot of error. So the answer to that question of, is it a lot, is, well, it's relative. It relates to what you're measuring. So often after you estimate the error, you then relate it to what you're measuring to say, is that a lot of error? Relative error then is the idea of taking your error estimate, which in the previous case would have been dV, and relating it to what you actually measured, which was the volume. That calculation, removing the plus or minus, is relative error. So if I were to find the relative error for what we just did, dV over V, dV was 288 pi, and the volume is 4/3 pi, and the radius was 12 cubed. We need to clean this up a little. The pi's drop out. It's 288 times 3/4 over 12 by 12 by 12. All right, so here we go. I know that 144 goes into that twice, and that cleans up nicely, and that cleans up nicely. So when it's all said and done, I get the relative error is an eighth, or as a decimal, 0.125. Sometimes, rather than a decimal form, they ask you that as a percent error. In that case, the percent error would be making that a percent, and you'd say 12.5%. That's a pretty good chunk of error. You're off by about an eighth of what you are measuring. That's, to me, substantial error. You didn't do very well, but we are eyeballing it. We weren't using tools, right? Now, last idea of using differentials before we do a little bit of practice. If you use differentials to estimate a new value, this is more of a math application rather than a science application, then it'll behave a little bit like a tangent line, but there's some differences. So if I asked you to say, use differentials to estimate the square root of 47, you want to know, all right, based on what you would normally start with, the square root of 49 is 7, you want to know how much are you going to change by going to 47. Well, let's use that idea. I want to use the change in y, or estimate the change in y, using differentials. Delta y can be approximated by this calculus idea, dy, which is f prime at a given starting point dx. Well, in this case, because the function is the square root of x, then the derivative is 1 over 2 root x. And our starting point is the clean point we're talking about at 49. The dx is the change. Now we're going from 49 to 47. That's a decrease of 2. Now that's going to mean a negative delta, which is logical because we're going to get a smaller square root by going from 49 down to 47. So when I do this, I get 1/14 times -2 or -1/7. That would mean then that my estimate of the square root of 47 is something like 7 plus some change, which I am estimating as 7 and lose a seventh by going down to 47. So my estimate would be something like 6 6/7 for the square root of 47. The delta y was approximated by dy. The dy came out to be -1/7. We use that here. We don't just stop at the dy here. In this case, we say that dy from where we started puts us at this new estimated value. All right. We ran out of time at this point and didn't get to these, but if you want to try these, they would be good problems to try because they will show up in your book later. But that should put you at least on equal footing with everybody else in the class, although they did take a small, short question quiz, one question quiz at the start of class. Have a nice weekend.